This isn't damage, it's just unscheduled hydroforming. Hello Internet, my name is Quinn and this is Blondihacks. I'm back on the Pennsylvania A3 switcher locomotive build this week, and I'm going to do something a little unusual in locomotive building. I'm going to pressure test the Firebox. As I've said all along on this boiler build, as much as possible, I want to unit test the sections of it to de-risk the possibility of the entire boiler failing a pressure test at the end, potentially wasting many, many months of work. So that's the plan. I don't know if it's going to work. This is not something I've ever tried before, but let's find out. Here is the Firebox assembly that I built in the previous video in this series, and the goal is to make sure that all of these joints on here, all these many joints, are all perfect, because if they aren't, then the final boiler will fail a pressure test and is thus no good. Now of course this structure sits inside the boiler, and thus the pressure is on the outside of this structure. I obviously can't test that. I don't have control over the Earth's atmospheric pressure, at least not yet, so I'm going to test this inside out. Which is fine. I'm going to put pressure on the insides of all these joints. Pressure test is valid either way. I want to do something along the lines of what I did when I tested the boiler barrel. I built a fixture that allowed me to seal the ends and pressure test all of the joints on this unit here of the boiler. I want to do the same thing, but the Firebox is a little bit trickier. It's a much more complex shape. In particular, the flat sides of the Firebox are problematic. Flat surfaces don't hold pressure well. The reason this works in the final boiler is because of these guys here. These are stay bolts. These tie the inner surfaces to the outer surfaces in a double wall, and thus makes the whole structure self-supporting against pressure. However, we don't have the stay bolts in place yet. My plan is to mimic the function of the stay bolts by supporting all the flat surfaces with thick aluminum plates that'll be clamped in place to provide the support. Because the goal is just to test the seams themselves and not deform the copper in the process. The other issue, of course, is that the foundation ring, or mud ring as some folks call it, is not in place yet. In this diagram here of the final boiler assembly, you can see how the mud ring supports the bottom edges of the Firebox by tying it to the outer crown sheet and so on. And then likewise, you can see all the stay bolts that go through both layers and tie everything together in a strong double wall. So that double wall isn't here, so we don't want to subject sections of the Firebox to forces that it's not designed to handle without all the stay bolts in place. On the back here are more stay bolts, which tell us those areas are vulnerable as well. In the center, we've got the fire door ring, which acts as quite a strong rib here that I think should strengthen that area, so I'm not very worried about that, but I do want to support above and below it. Of course, the big opening at the bottom here needs to be sealed, and that's going to be the primary challenge. This is a complicated shape, so I can't just mill a square groove in a plate and seal it up that way. I'm going to need to do something else. I think I'm going to try using a flat gasket first. I think that'll be easier than trying to machine a complex groove to seal that shape there with all of the inner flanges and so on. I dug through my aluminum scraps and I found this chunk here, nice and thick. Should be more than ample to support the sides. Hopefully I can get all the pieces I need out of this. Then of course I'm going to have to seal the fire door opening there and the tubes at the other end, but those should be easy. For all these sealing jobs, I picked up this stuff from McMaster. It's 1/8 inch thick gasket sheet stock. It's quite soft and quite thick, so I should be able to compress it as much as needed to take up all the imperfections in all these weird sealing surfaces that aren't really sealing surfaces. To start with then, I'll cut up my piece of scrap here and hopefully get all the pieces that I need out of it over on the bandsaw, and I did pretty well. I got most of them out of that, I think. I'm being very approximate with the dimensions here because, well, this is the scraps that I had, but I don't think that'll matter, right? Right? I need to trim this down a little bit on the front here to get under the tubes there. Now I need to make holes for the stay bolts because I need to support the flat sheet behind them. I'm marking the height here of the row. I'm biasing this towards the bottom with the assumption that the tubes will support the top third of that sheet there. Then over to the mill to punch those holes. I'm using generous clearance holes here. I want the plate to go around the stay bolts without actually touching them, because I want to be able to see the joints inside the stay bolts, because of course the joints on the stay bolts are part of what I'm testing here. One of the many goals of this fixture is to support all the copper, but still allow me to see all the joints so that I can see if there's water leaking out anywhere. Conveniently, getting the spacing on these right is easy because of course I know how far apart they are from the boiler drawing itself, so I don't have to measure anything. Quick test fit here on the stay bolts. And that fits nice, but it does not sit flat on the sheet, and that's because of the fillet created by the silver solder around those. So I put a very, very generous chamfer on the insides of those holes so that the plate will sit flat. If the plate doesn't sit flat, it's not going to support the copper sheet behind the stay bolts, which is the entire goal here. That sheet will distort if that plate isn't right up against it, and that looks really good. For the back, I dug through the scrap bin and I found this. Used to be a fixture plate for an eccentric strap, I think. And conveniently, it has a slot in the top that's already going to clear that top stay bolt. And it looks to be the perfect size for making a back plate here. So I think I can make this work. It's a little bit thin, but because this side has the fire door ring, it doesn't need as much support, I don't think. So I think this will be fine. I marked the height of the stay bolts there. And I'm going to measure the diameter of the fire door ring, because I'm going to have to punch a big hole in this plate to clear that ring, of course. And then I marked some center lines on there just to get everything roughly aligned. I used the DRO on the lathe to actually position all these features, again using the boiler drawings to figure out where everything goes. Fun fact, the reference center for this stay bolt pattern does not actually have a hole at that position like the other pattern did. I realized this halfway through drilling this hole, so I aborted, and we have half a speed hole in the middle of this pattern. Shouldn't hurt anything. And then I proceeded to drill the 3 actual holes around that position. Imperial fist shake of mild frustration, and proceed. Northward from there then, we need to make a great big hole for the fire door ring. Now this hole does not have to be pretty or accurate, so in with the big guns. I'm going to use a hole saw for this. Hole saws are the sledgehammer of hole making tools. They are not accurate and they are not pretty, but they sure are fast, as long as you don't care exactly what happens. With a cutter this aggressive, I'm not shy with the cutting fluid. For aluminum I use WD-40, makes excellent cutting fluid for non-ferrous metals. And away we go. I'm running this probably a little bit on the fast side just because I want to get that pilot drill through there with reasonable efficiency. I'm probably going to have to slow it down once the teeth engage. And yeah, sure enough, that is chattering quite a bit, so I'll slow that way down. And let's try that again. There we go. Now it's cutting like the metal-eating monster that hole saws are. Whoop, it's also occasionally stalling the spindle. Not the motor on my mill, just the spindle. I keep the belt on my mill just a touch on the loose side for exactly that reason. If something gets overloaded, I'd rather the belt slip than strain the motor or potentially burn out the driver board. As expected, that hole is ugly and oversized, but it appeared very quickly. And that will be just fine for this use case. I'll do a little test fit here. Everything looks like it lines up extremely well, except, whoopsie, I forgot to account for that little strap that's on the top of the fire door ring there. I'm going to have to make clearance for that. So I marked out its position there on the block there, and I'll go back to the mill and mill that out. And I just kind of etch-a-sketched this out, eyeballing it to the line that I described there. It's nice when things don't have to be accurate. You can just kind of wing it with the hand wheels and have a little fun. I mean, not that machining isn't normally fun. Of course it is. That's why we're here. Take 2. Let's see how we did. And, ooh, look at that. That is surprisingly satisfying. Once again, I put counter bores on the backs of the holes there so that it'll sit flat on the back sheet, and that looks really good. To seal the fire hole, I've got this scrap here, and this was actually the mandrel that I used to hammer form the fire door ring. It's tempting to use it as is, but I think it would risk over sealing the hole. I don't want to seal the whole thing, I just want to seal the very front edge of it here, because I want to make sure the entire seam of the strap there gets tested by the pressure test. So I want to seal basically as little as I can. So to that end, I think I can use this piece, but I'm not going to use the whole thing. It's got the handy threaded hole in it, so I'm just going to chop the end of it off and use that. Over to the lathe then to part this guy off. And Yahtzee. Then I'll face that down to make a good sealing surface there for the gasket that's going to go on there. A little deburring, and that should make a really nice sealing plug for the back of the fire door ring there. For that to actually seal, of course, we're going to need a gasket, so it's time to bust out that sheet stock that I talked about at the top. I could have used the paper gasket stuff that I have for this, like I used for the steam dome base, but all of these surfaces on the boiler are all hammer formed and hand filed and hand fitted, so none of the surfaces are especially great seals. So I think this thick rubber material is going to be a lot more forgiving than the paper stuff would be. I'll need a hole in the center, of course, so to my tack hole punch, which I love very much, one of my favorite secret weapons in the shop. And of course I do enlarge it a little bit with a knife because the largest size was too small for the 1/4-inch bolt that's going to go through this whole assembly here. For the other side of that, I machined another disc, and I've got an extra hole in it there, and that's because I don't want to accidentally seal up this side of the fire door. I want the fire door ring itself to get filled up with pressurized water, again to make sure that the joints within the fire door ring there also get tested. Otherwise I could accidentally just create an airlock here and no water or pressure would ever get in there. With the fire door sealed, I'm going to turn my attention to the bottom now. My plan is to reuse a lot of the components from the barrel testing that I did, and that includes these end plates here. They're actually already a good size, and I can reuse the bolt holes there for clamping. So I think I should be able to place the other one on top of the firebox like so and clamp between them. The plumbing fixtures will actually go on the bottom so that they're feeding into the opening there, but this is just a mock-up. Now the challenge though is I don't want to clamp just on the top ribs there. I want to clamp on the entire top of the crown sheet so that I don't risk damaging or deforming something there. And I also want the top of the crown sheet to be supported for the pressure. So I measured the distance there, and I'm going to make a little filler piece that's going to sit between those ribs and fill up that space. I've got this piece of scrap here, which is pretty close to start with. I'm going to start with a ball nose end mill, and I'm going to cut a curved trench down the center of this thing to kind of match the radius of the top of the crown sheet. Now, of course, this ball nose is a much smaller radius than the crown sheet is, but by creating a curved feature here, I'm going to get 2 points of contact on that crown sheet instead of just one as I would with a flat sheet. So even though it doesn't match the radius, I'm doubling the amount of support here just by making a smaller radius feature. You'll see how this fits here in a minute. The piece is also overall overly thick, so I also milled down the sides there a little bit further with a regular end mill. Here's how I hope this is going to work. You can see how that curve sits on top of there and fills in that space so that the clamping plate will sit flat there across the center and on those ribs and hopefully provide nice even support all the way across there. That's the idea anyway. I honestly have no idea if any of this is going to work. With the top sorted then, I'll move to the bottom and I'm going to make the gasket that will seal the bottom of the firebox here. I'm just going to make a straight rectangular gasket and make it overly wide so it'll just cover all of the weird sheet metal features that are on the bottom edge there as I showed at the top of the show. Again, I'm counting on the overall ductility of this gasket material to just take up all the weirdness in the sheet metal that I have to try and seal. I'm also opening up the center here, both because the plumbing fixtures need access to the middle, of course, but also because I think it will seal better. By making a ring instead of a flat sheet, local areas of the gasket can distort as needed to conform to the sheet metal in that area, whereas if it was a flat sheet, then if one area needs to pull or shift a little bit, it's going to pull the opposite side of the gasket out of alignment in order to form to the surface. Let's talk plumbing now. This was the steam pipe cap that I made for the barrel test. I'm going to reuse it as a plumbing fixture to fit the check valve that's going to feed the water into the system here. The other hole there where the speed hole was on this plate is being used for the pressure gauge. So once again, I'm reusing as much from the barrel test as I can to save myself a lot of time here. So this was very easy. I just tapped and drilled this out and I threaded it for the fitting. I don't need this fitting for any other purpose anymore, but if I did, I could still use it for its old purpose by just putting a 1/4 40 plug in the end of that and it would seal up just fine. So that now threads into there, and that threads into there, and there's my check valve for the input water. Here you can see how this is hopefully going to work. Those two plumbing fittings there open up into the bottom of the firebox. So that's how the water is going to get in and how we're going to measure the pressure. The last thing to seal up is the ends of the smoke tubes. Those should be pretty easy. I've got a chunk of aluminum here from the scrap bin, and I'm going to make 3 little plugs to go in the ends of the tubes and plug them up. Once again, I'm plugging the ends of the tubes, not the base of them inside the firebox, because I want to make sure that all of the tube joints also get pressure tested. Once again, the goal is not to test the structure of the boiler. That's built to Kozo's design, and he knows what he's doing. The goal is to test my silver soldering. So the goal is to expose all of the joints that I made to the pressure. The copper itself is built to specification, and it is strong enough. I don't have to worry about that. All of these plugs, as you may have noticed, are blind threaded holes. That way I don't have to seal up the threads. And of course, we need gaskets for these plugs as well. Let's put it all together here so you can see what I'm thinking. There's threaded rod that's going to run all the way down the length of the smoke tube and clamp from the other end. You might be tempted to use some sort of tapered plug in the end there, but I intentionally did not do that because I don't want to risk deforming the end of the pipe as I clamp down on it. So I figured a flat plug on the end of the pipe is safer for that reason. Remember, all this copper is quite soft because it's been heated a lot. On the inside there, I've got an intentionally loose-fitting washer, again to make sure that water can get past that and into the tubes so that the tube joints are exposed to the water and the pressure on both sides, and also so there's no airlocks in anything that can interfere with the hydrostatic test. I think I have all the pieces now, so let's start mocking things up. Final challenge is how I'm going to clamp everything. I've got to make sure that I can physically get all the clamps in here in a way that they're not going to interfere with each other. I've got the bottom and the sides and the front of the tube sheet there and the back plate there. Well, first lesson, there's an order of operations to assembly here. This plate does not clear the gasket on the fire door ring. That's okay, this is just a mock-up. Threaded rods then are going to go down through 4 of the corners here. Again, very similar to how I clamped up the barrel. That worked really well on that setup. Now I should be able to put my F-clamp on the sides and my C-clamp, nope, F-clamp front to back because I need more reach there on that. And then C-clamps on the sides seems to be the ticket. And then there's still clearance on the top there for the top plate. Okay, I think it's going to work. Let's try this. I redid all that for real, actually tightening things. And now let's get the gasket in there. I had to clearance it a little bit for one of the plumbing fittings, as you see in the corner there. And now let's get the top plate in position. I went around and snugged up the corners there evenly and gradually. I'm kind of watching that gasket underneath and watching it compress. You can kind of get a sense from visually and also how tight the bolts are getting when it's probably enough compression to seal. But again, I'm trying to tighten these up as little as possible, same as I did with the barrel, in order to seal pressure but not risk crushing or distorting any of the copper here. All right, let's fill it up with water and see what happens. Of course, I'm checking to make sure it's actually watertight first. That's the first test for any boiler structure. Sometimes they don't even hold water when you start doing these tests, but this does seem to be holding, so that's good. And yeah, don't do that when you're filling a boiler for a hydro test. If you spill water everywhere, you have to clean it all up. You have to get everything spotlessly dry, because otherwise, when you see water, you don't know if it came from somewhere in the boiler or if it's just leftover water. So best way is just don't overfill it, be very careful, and don't get a drop of water anywhere outside the boiler before the test. Then a check valve goes in, and hopefully we can start pumping pressure in now. I was a little concerned that the check valve wouldn't work properly sitting horizontally as it is there, and my suspicions were shortly confirmed. I was able to pump the boiler full all the way up with the pump here, and then pressure did start building, but much like when I was testing the barrel, if the check valve isn't sitting vertically, then it doesn't really work properly, and on every backstroke of the pump, all the pressure that you've built just bleeds back through the pump. I didn't plan ahead for that very well. Because of the orientation of the clamps, I can't sit this thing vertically. However, I was able to get it at a bit of an angle, first a little, then more, and with enough angle, the check valve started working. So I got away with this, and I was able to build up to 75 psi, as you can see here. So I stopped here and started checking all of my gaskets and seams for any signs of leaks. It's holding that super well though, so I decided to get a little greedy and I went up to 100. I'm not going to test this to 200 because I don't think this fixture can handle that. I don't want to risk damaging the firebox here. But 75 went so well that I went to 100. I was honestly going to be happy with 60, but you know, here we are. Things are looking really good. No moisture anywhere, and the pressure is holding for several minutes. I'm really impressed with this gasket, I have to say. That thing is sealing like a champ on a very imperfect surface. So strong recommend for this 1/8 inch gasket material. There is some sign of trouble here that I didn't notice at the time though. Look what those fire tubes are doing. Those aren't really straight anymore, are they? See how they're flaring out a little bit? Yeah, more on this in a minute. At 100 psi, I started to get a little seepage on one corner of the main gasket there, but snugging up that corner there seemed to take care of it. Everything looking good there. And well, I just kept getting greedy, so I thought, well, 100 worked. How about 125? So I went up to 125 psi. This is now more than double than I intended to test to, and we're now at 1¼ times working pressure for the boiler. So this is a very substantial test. 125 though is when I noticed the problem that on video was visible sooner than this, and that's the flaring of the tubes. You can see it's getting quite dramatic now. What's clearly happening here is that the front tube sheet of the firebox down in this area here is starting to dome out. It's distorting under the pressure because it's not well enough supported. Again, this system is not designed to take pressure in isolation like this. It's designed to be part of a larger assembly that's supporting everything. In the case of the tubes, the front tube sheet is supposed to be there, which helps support everything. Well, I know to quit when I'm ahead, or at least not too far behind. I don't want to damage the tubes any further there, and now that those tubes are distorting, there could be other things distorting that I haven't seen yet, so definitely time to quit, but I'm really happy with that 125 psi test. I tried to loosen the check valve there to bleed down the pressure, but in a tribute to Loctite 545, that didn't work. I wasn't able to release any of the 125 pounds without risking blowing that fitting out of there by undoing it all the way. However, what did work was just loosening one corner of the main gasket there until I started getting a spray of water out of there. That bled down the pressure in a nice, gradual, controlled fashion. You don't want to bleed the pressure down too quickly because it'll stress the pressure vessel and, more importantly, cover you and all of your shop in pressurized water. With the pressure relieved, I can now disassemble the threaded rods here and pull the top off. Here's our gasket there. You can see it's still full of water, so everything seems to have gone well here. Take the gasket off and oh, look at that. Look at that distortion. That's super interesting. You can see how it ballooned out there right above the supporting plates there. I should have had those supporting plates a little bit taller, as you can see. I pumped a little bit of water out of there so I can dump the rest out without making a huge mess. Well, my instinct about having to support everything was correct, as you can see. Just above where the plates stopped is where it bowed out on both sides. That's super interesting. As one of my patrons said, this isn't damage, it's just unscheduled hydroforming. This certainly illustrates the importance of the foundation ring for supporting this bottom edge under pressure. Luckily, this is still annealed copper, so it's easy to fix. I just squeezed the sides back together there with the plates and straightened them back out. I'll probably do a little bit of hammer and dolly work there to straighten them out and take out some of the wrinkles there, but no harm done. Copper is extremely forgiving with all this sort of thing. All the other support plates seem to work really well though. No distortion on the back or on the lower part of the tube sheet there. Fire door sealing ring worked really well. Let's get a closer look now at that tube sheet damage. The tube sheet actually still looks flat. The distortion is so minor that you can't even see it. It still looks perfectly flat, but the tubes are so long that the tiniest little bit of distortion at the base is enough to cause the flaring that you see there at the end. I think this should be pretty easy to fix though, just like the sides were. I'm going to use the front tube sheet here as a jig of sorts and force the tubes back into alignment. So I squished the front tube sheet on there, hold them in the correct positions, and then I kind of just gave the middle of the tubes and the base of the tubes there a little bit of a squish to kind of set their position right here, just like they're supposed to be. And that seemed to work just fine. I wondered if the tubes had maybe bent and that's why they were flared, but no, they're still straight. So it was just the front tube sheet there doming ever so slightly under the pressure, which again wouldn't happen once the boiler's fully assembled because everything is properly supported. But that little squeeze gave them the fix that they needed and everything is nice and straight again, like it never happened. Well, that was a wild ride, but I'm really glad I went through that exercise because now I have a lot of confidence in all of these joints. which is important because in the final boiler, most of these joints on the inner firebox area will be inaccessible and thus impossible to repair, especially those inner tube joints. If those weren't sound, and the final boiler is assembled and fails a pressure test, the whole boiler could be scrap and thus waste hundreds of hours of effort. For the final hydro test of the entire boiler, of course, all these joints will be pushed to 200 psi, which is 2 times working pressure. But getting to 125 psi with this fixture now really gives me 99% confidence in these joints, and that will help me sleep at night as I finish the rest of this boiler. Well, that is all the time I have. Thank you very much for watching, and I hope this was interesting for you. Thanks especially to my patrons who make all of this content possible, and I will see you next time.